Hi everyone. Today in this class I'll teach you about predicate calculus. By predicate calculus I mean not calculus as such. It has nothing to do with calculus. Okay, what we do is, given the compound propositions or premises, we make arguments using the rules of mathematical logic and arrive at a conclusion. That conclusion need not be as given in the book or as they expected. As I told you that when a lawyer argues his argument, he makes an argument with the proof or evidences given by the witness and there is the convict, and he argues on the points and comes to a certain inference. He makes an inference and the judge takes all the inference with him and finally sorts out, or he analyzes fully and comes to a conclusion and he gives it as a judgment. So this is what we are, that is verbally doing, and here we apply the mathematical principles, mathematical logic here, and arrive at conclusions given the compound propositions. This is what we have done. But let me start with an example like this. I write something here. See, P of x. See, P of x, see, for example, first I'll write x greater than or equal to 5. I write something here. Before I explain this x greater than or equal to 5, I will explain what is a proposition. I will try to recall what is a proposition. See, I write this. I write on the board. Now you tell me whether it is true or false. It is true. I write on the board poetry. See, yeah, that sentence may be correct. I write on the board a poetry. It is a correct sentence. It is by sentence wise, it is correct. But whether it is true or false, it has to be understood on seeing what is written on the board. Here on the board, I do only mathematics. So that statement is wrong. The statement may be wrong, but it is a well-written sentence and it is called a proposition. A proposition is a simple sentence for which you can say either yes or no, false or right, right or wrong, something like that. Okay, success or failure, something you can give, only dichotomous. But here in this case, I write on the board means yes, I write on the board. Now here it is well understood. You can say that it is a proposition. So unless something is understood as a proposition, you cannot keep it with you and use it for some argumentative purpose. You cannot do that. Now keep this in your mind, and now let me come to this x greater than or equal to 5. Now, what is that x greater than or equal to 5? See, what do you mean by that? X, is this a proposition? It cannot become a proposition unless and until you know something about x. So it is not a proposition at all. This is not it is maybe a propositional function. It is called a propositional function. This is called propositional function. X is greater than or equal to 5. I say that it is a propositional function, or I call it. Better have that in your memory. Propositional function. But it is not a proposition at all, because it is not conveying you anything. Can you say yes or no for this? No, you cannot say either yes or no for this x greater than or equal to 5 unless I define what is my x. I tell you what is my x. I write something here. Say I write a is 5. See, 5, 6, 7, like this. Say I put this all natural numbers greater than, I take a set, and I take the set which consists of elements 5, 6, 7, 8, 9, like that it goes on. Now I tell that this x is greater than or equal to 5 and x belongs to A. What is that I do? I say that x is greater than or equal to A and x is a member of the set A. Now you see that you give 5. So what are the numbers available to you? 5, 6, 7, 8, like that it goes on. So every number will satisfy this. So this is now it becomes a propositional, it is a proposition. A propositional function has become a proposition on assigning value to the variable. This is a variable, x is a variable. Now, so you see that x greater than or equal to 5 is not a proposition unless and until x is defined. I say that x is some number which is taken from the set A defined by this. Now, if you define this set and you say that x is a member of A, then naturally that x greater than or equal to 5 becomes a proposition. Till then it is not a proposition, it is a propositional function, and x is a variable. It is it can take 5, 6, 7, like that. Now this I put it in this way, that is p of x. Now I put this as p of x greater than or equal to 5. Now you see that, now read this. I write p of x. See, I write something p of x. What do you understand by that? So x is a variable and p is a predicate. We call them as predicate in the sense that it gives what is the property of that variable. What is being talked about that variable is called a predicate. So this is called predicate. This is called predicate of x. Predicate of x in the sense that x is a variable and x has got the property. Now I am talking more about x. I am talking about x. So I am telling you what is the property of the x. What is x? X denotes the property of x. Yet x means it is a variable which is greater than or equal to 5. So p tells that x has the property that it is always greater than or equal to 5. Therefore this p is called the predicate and x is a variable. Now this is a propositional function and it can become a proposition only when you assign values to x. Can you understand? So this p of x is a predicate of x, and it means that, and you can give more examples on that. Now let me come to this. I will finish off this and come to that. So p of x means x has got the property that, what is the property being told by p? P tells that it is a number greater than or equal to 5, and therefore I understood x is a variable, p is a predicate which talks more on x. And so this p of x greater than or equal to 5 has got a meaning here. So I am defining it like that. Now it means that x greater, but still it has not become a proposition unless and until the x is said where. That is, x is clearly defined. Now x is a number which is taken from the set A, 5, 6, 7, 8, 9 like that. So you see that any number you assign there is satisfying, and you say that P of x is x greater than or equal to 5 is identically equal to t. What is the meaning of that identically equal to t? That means if I say that is identically equal to t means for any value that you assign for x, if this is true, it is true. You take any value from A, it is true. What does it mean? For all values. So I say that I can put this as for all x. This means for all. For all x. So for all x, P of x is greater than or equal to 5 and x belongs to A. So what does it mean? X is taken from the set A, and whatever the value that you assign for x, it satisfies the condition that P of x greater than or equal to 5. Now this is a proposition. It becomes a proposition. Now, so this is a propositional function, and this, and you see that this is called a quantifier. That means what? That predicate has been quantified. Quantification means there are only two quantifications that I can talk about. One is universal quantifier. Universal quantifier. This is written as for all x. This is a symbol that you must use. For all x. Some notations are also there, but let us use this. For all x means what? For every x. From where do you say take this x? That is a different thing. Now, so for all x. Another one is, say another one I'll write here. Existential quantifier. So what does it mean? Existential. See, when you read anything, particularly in mathematics, you must clearly understood what is said and analyze them and apply, and that is you do some introvert work, in the sense that you think internally and get into your mind, discuss things and come out with clear-cut ideas. Unless then you will not be able to do mathematics. I tell you, it's very difficult. So you see that everything has got an importance, that you must understand everything. So what is that here? It is said it is for all x. For all means for every. For all means what? Every. And here you see that if I write this, there exists x means there is some x, not all. A few x. A few x. That means for a few x, it may be true. The propositional function may be true. That is what I understand by that. So here it is means for every x, there exists means for some x. A few x, for a few x's, it is correct. Now, I will come to this. Say, what is the meaning of this? For all x, P of x greater than or equal to 5, for x belonging to what? This set A. Now you tell me whether this is true for all. I have written here, P of x greater than or equal to 5 is identically true, means it is true for all x values, it is correct. Okay, now therefore this for all x means for every x. It is called a universal quantifier, in the sense that that particular propositional statement comes true for every x taken from the given set. That is called proposing a universal quantifier. Now, I hope that you have understood. I will pass on to the next step. What I do here is that I'll take another set here. See, for example, I take very simple. Understand, and you write that 4, 5, 6. Now, what is that I have done here? I have included one number. I have taken one more number, 4. But you see that for this particular set, I say that now you forget about this. I write this statement. See, I write this statement, and instead of this, I put it as what? I put it as x belongs to B. What is that I do? I write x belongs to B. Now x belongs to B. Now what does it mean? X belongs to means what? It is a variable, and I say that for every variable x belonging to this set B, this statement. What is that propositional function given to you? P of x, x greater than or equal to 5 for all x belonging to B. Now you see that whether is it true? Is it true? It is not true, because you can find at least one x. What is that? If you find at least one x for which this statement is not true. So you see that P of 4. 4 is, what is that? P of 4 means what? 4 has got the property that it must be greater than or equal to 5. Now you tell me whether this is true. This is not true. That means there exists, now I'll write here, there exists an x, x belongs to B such that x is not greater than 5. Correct or not? So x is equal to 4 is what? A number which does not satisfy this particular condition, predicate propositional function. It is a proposition. Try to understand. It is a proposition. It is false or right is a different thing. I am not bothered about that. Whether it is a proposition, yes, it is a proposition, but does it satisfy that? It does not satisfy. That means there exists at least one x for which this particular statement is not true. You write this as there exists. That means what? At least one or a few. One may be there or many numbers. If I add 3, 4 like that, it means that what? More numbers are present. Can you understand? You see that, for example, I will put it like this. You can put this one, no. You can take any example. Let me not elaborate on that. You see that you can give any number examples for that. And you see that this is what I will write here. See, P of x, x minus x whole squared is equal to x squared. And you see that this minus x whole squared I write it as what? Minus x whole squared. So what is my propositional function here? P of xy means what? P of x means what? X is a number which has got the property that minus x whole squared is equal to x squared. Is this a correct statement? Yes, it is a correct statement. Suppose if I write that my P of minus x squared is equal to minus x squared, it is false. It cannot come, because the square of any negative number or a positive number is going to be a positive only. Now you see that this is true for any value that you take from the set of all real numbers. Okay, set of all real numbers means what? A real number consists of integers will be there, rational numbers will be there, and irrational numbers will also be there. That is called a set. So a real number is a set in which you get all integers. Integers means negative and positive natural numbers. And you see that you get 0 there, and you get rational numbers and also irrational numbers. For example, square root of 2, it is an irrational number. So like where you get that perfect square is not, or decimals or numbers are there, we'll be calling us irrational numbers. So you see that this is true for any number like that. Okay, now so you see that this is what mean. So we have taught you about what is a propositional function. What is a propositional function? And what is the meaning of a quantifier? A quantifier, there are two types of quantifiers. One is universal quantifier, another is existential quantifier. Universal quantifier is one which says that for every value assigned for that variable, then it becomes an universal quantifier. Existential quantifier means that that particular statement given to your propositional function is taking a truth value. It becomes a true only for certain values of that variable. And importantly that you must know is, the question is, from where do you take this x variable, the values of the variables, where do you get from? Where do you get from? You get it from somewhere. That somewhere place is called your universe of discourse. See, this is called a universe of discourse. Then what is the meaning of that? Nothing. There's a universe of discourse is a domain from which you take the values for the variables x. As I told you here, B is this. Now your universe of discourse is what? B. In the previous A I gave you without this 4. So A was your universe of discourse. So universe of discourse is the domain from which you take the elements to assign the values for the variables. Are you able to understand? So this is all about this. So predicate calculus means where we deal with predicates, that is a propositional function like. That means you have got, and where you propositional functions also quantified. Quantification only what? For all and there exists. So these type of quantifications will come in the predicate calculus. As we have done for statement calculus, the inference theory, here also we will apply the inference, that is we will use in, that is we will apply inference theory for the predicates also, and that is called your predicate calculus. We are going to apply for the predicates also. That means what? Not plain statements, propositions, not plain. This is not a plain proposition. Can you understand? Here you see that x is a variable. Unless you are given this meaning, this x greater than or equal to 5 has no meaning at all. I must say that p of x means x is a variable. It has got the property that is. Then it becomes a propositional function. Only when values are assigned, it becomes a proposition. We take such propositions where they can be quantified also. We take them, and such statements, propositional statements will be taken, and we do the arguments as we have done in the statement calculus and arrive at the conclusions as before. So this is what we are going to do here also. Before that, I'll come to this. See, for example, see, I write something. It is not, see, this propositional function, it is not confined to one variable. I don't confine to one variable. I can write like this. See, I put it like this. And what is that understanding? Now you see that it is a proposition. See, there are two variables coming, g of xy. G of xy, you can give, see, that means what? This x and y are variables. X and y are variables. And something should be said about x and y. What is the relation between x and y? You write x and y, unless there is a relation between x and y, you cannot write like this. See, you put they are not two different things. They are two things which has got some connection in between. So that is what I do. So g of xy means what? Now g will tell you the property of x and y and how they are related. Say for example, I write that g of xy or b of xy or s of xy. See, I mean that x is a number greater than y. X is a number greater. So that is it. So g of xy, it means x is greater than y. It's this thing, a propositional function I am giving. And here it means what? B means x is brother of y. S of xy means x is sister of y. So you can give propositional functions like this. So here the difference is that there you studied about plain propositions, but here propositions are, that is variables are given and the properties are being said. Such things will become propositional function, and they become propositions if the values of the variables are known. That is what we have done. Now, so this is what we are doing, and you see that here what I do here is that, see, I put like this. I put something here, you see. See, I say that, see, for example, I say that as I gave you the first example, p of x is greater than or equal to 5 and your a is equal to x1, see, sorry, this is 5, 6, 7, 8, 9. Let me go up to say some 20. Okay, no problem. Now let me take number of finite number of variables. Let us take. Now you tell me for every, what does it mean? This is for all x. For all x, p of x is identically true. This is very much correct, because any x you take here 5 or 6 or 7 up to a20, that is, this particular statement is valid. Now for that, if you say that for every x a particular propositional function is true on assigning the values for the variable, then it means that, see, that means this implies that p of x1 is true, p of x2, p of x2, see, intersection p of x3 dot dot dot, let me put it as even pc of x2, whatever it is, p of xn must be equal to true. What does it mean? Here also you must put here intersection. So conjunction, that means what? For p of x1 it is true, for p of x2 it is true, for p of x3 it is true. Up to anything that you take, it must be for every x, this p of x1 intersection, conjunction, p of x2 conjunction, p of everything must be equal to your t. Then only we say that it is a universal, that is, for all x's is true. Okay, but if I say that there exists, if I say that what? There exists, if I say that there exists x, if I use that quantification, that means I will rub off here, say I will use this here. So you see that if I use there exists, if I use that there exists p of x, then this implies that p of x1 union p of x2 union, it is disjunction p of xn. That means what? Here even the meaning of this is, that is, if I write this, even this t let me not take, if I say that for all p of x is true, that means what? This must be true, this must be, everything must be true. Okay, that is, if I say that for all x, p of x means p of x1 conjunction p of x2 conjunction p up to conjunction p of xn. But if I say that there exists p of x1 means p of x1 disjunction p of x2 disjunction p of x3 disjunction up to, it goes up to this n values p of xn. Now you see that what does it mean? I told you that if it is for every x, then for all values of the variable x, this must be a true statement. This must be a true statement. Or you can say that for all values of x, that is also false. For any value you take, that is going to be false. But if we want to negate it here, what does it mean? There exists an x, p of x means, see, I have taught you, if you have listened to my lectures very closely, I would have said that, say, I teach in the class and you listen. This example I had given. I teach in the class and you listen. Now, what does it mean? I teach in the class is P and you listen. Let us suppose that your P stands for I teach in the class and you, Q means you listen. What does this mean? If you take, even if one is true, the whole statement is true. What is that? If one, there are two variables here, two propositions are given, and even if one proposition is true, it is true, because we have studied about the truth table for what? If there are two variables, I told you that 4 rows will be there, TT, TF, FT, FF, and for out of the 4 variables, only when both P and Q are F, you get the truth value of P union disjunction Q to be F. I have taught everything, and you can just go to my videos and watch. Okay, I will give the link in the next class. So you see that this is what I have done here. So now, so either P or Q means, here this is that means either P or Q is true. How do you read that? P or Q. Either P or Q. That means even if P or Q, not necessarily both, even one is true means the whole statement becomes true. So I teach in the class and listen. I don't teach in the class, but you sit and listen. I teach and you just keep quiet and you may not even listen. So that is so. But I don't teach and you don't listen means you are not. That means what? False. So you see that here this P and Q, even if one of them is true, it is true only. So you see that here everything is true. So you see that here what happens is that if you have at least, let us suppose that in this particular problem, what I did was, I took the set B, which is equal to what? It is 4, 5, then it is up to 20, let us say. Now you see that for P of xi, it is identically true except for what? Except for x is equal to 4. X is equal to, that means what? This statement is, that means what? You can say P of x1 disjunction, P of x2 disjunction up to P of x2, it is equal to 2. It is there. But at least this one value will become F. All others, this one. So it may be a true statement, but what I tell you is that if you want to say that, for example, let me suppose that you are writing, an engineering student writes all 8 papers, and you see that if he wants to, let us suppose that he is coming out of the college, and if you say that he is a qualified engineer, that means what? He has passed out in all the subjects at least with the minimum marks. But if you say that he has not become an engineer, that means what? He is not qualified, he has not passed out all his papers. That means even if there be one failure, he is not an engineer. He has to, let me not score 80 or 90% in that. He has to score the minimum marks. If he scores the minimum mark, he comes out. So you see that an engineer is supposed to be called as an engineer only when he passes out, he scores the minimum marks in all the subjects, But even if there be one subject in which he fails, means he is not an engineer at all. So that is what. So this is true means for what? It is true means for all values of true, T must be true. But if you want to say that it is false, means you say that, I say that what you are telling is correct, means if I find at least one thing which is wrong, then whole thing I say that you are wrong. I don't accept it. So in order to prove yourself to be good, you have to be good everything. If I say that you are bad, means even if there be one bad thing, even 100 good things may be there, but even if there be one bad thing, I will call you as bad only. So you see that just like that, here this statements, even if you want to prove that it is a false statement, means at least then even if there be one F, the whole thing becomes false. But if you want to prove that it is true, means what? It must be true for P of x1, P of x. That is why I write P of x1 intersection P of x2, and here it can be false also. So this difference you must know. What I want to finally drive at is that if you want to prove that something is for all, means for every element. If it is their existence, means what? For at least one, it is false. So if you say that, the whole thing becomes false. Okay, so that is what I mean here. I want to drive it. And let me come to this. See, there are, we have, that is, we have in propositional, in statement calculus, that is propositional calculus. What I mean is that we studied about propositions, and that is called a propositional calculus. Here I had taught you about what is a predicate, and this is called a predicate calculus. In propositional calculus, you have come across what is called statements like P implies Q. Q if only P. Now likewise I can talk about here P of x implies Q of x, and you put this, and if you put this for all x, what does this mean? This for all x, P of x implies Q of x. Q of x is true only when P of x is. That means if I say that he is, let us suppose that P of x, you can give x P of x, say let me for all x let me write this as C of x. I will put it as okay, so no problem. Computer science. Say for example, I'll take like this. I'll put it like this. Let me put like this because I'll give you a specific example on this. Say for example, I write this, even I can put this way. I will put like this. For all x, see I write here what is that I write? For all x, C of x implies discrete mathematics. That means what? X is a student of computer science. X is a student of, so what is this x? So C of x, if I write, it means that x is a computer science student. So for all x, C of x means, for all x, C of x means for every student, a student of computer science engineering, then implies that discrete mathematics. That means he learns discrete mathematics because he has to necessarily, a computer science student has to necessarily learn or study this discrete mathematics. So if you are studying this discrete mathematics in engineering college, this is an example I am giving you, then automatically he means that he must be a computer science student. So this means that for all x, and you must know that here this is not a propositional function, this is only a statement. Discrete mathematics studies discrete, that is a computer science student studies discrete mathematics. So that is a proposition, that is not predicate, it does not come under this thing, that is like this for all x and everything, it does not come like that. This is a plain statement. I make a plain statement. What is that? A student studies discrete mathematics. So here you see that if a student studies discrete mathematics in the engineering college, it means that he has to be a computer science student. So you see that for all x belonging to C of x means what? For every student who studies, who is doing his computer science engineering, then he has to necessarily learn this discrete mathematics. So in engineering college, if he is learning discrete mathematics, means he has to be necessarily a computer science student. So you see that this is how we express. So for all x, so here it is different. Here what I mean is that here it means that for all x, see, for all x, P of x implies Q of x. This is we have come across P implies Q. One way implication we have given. So you see that this for all x, P of x implies Q of x. This is coming in predicate calculus. This is coming in the propositional calculus. So you see that P implies Q, the meaning of this is, as I told you, keep all these things in your memory. So this is identically equal to negation of P union Q. The same thing here also it is true. For all x, it is negation of Px disjunction Q of x. So the same meaning it has got. The same meaning he has got. Now, see that, now I say that this P of x statement and Q of x statement, they are bounded. That means what? They are controlled or bounded. So these are all called bounded variables. This is called bounded. That means for all x, p of x implies q of x. Now if I write like this, for example, if I write like this, for all x, p of x implies q of x conjunction or of y. I will simply write like this. Now you see that for all x, I put it like this, you be careful with this. P of x I'll write it clearly so that you will understand better. Now you see that I have written something here. See, for all x, p of x implies q of xy. Here you see that there is one more variable that has come. That will be, let us not bother about that. Let us say that there is a variable, and that variable has gone an importance here and it plays a role in this. Let us not bother about what it is, because I am giving an example. So you see that for all x, p of x implies q of xy. You see that for all x, x is a variable which is bounded in the sense that they are, that is, this is controlled, that is your p of x and q of x is being controlled by this for all x. That is called a bounded variable. But this particular variable, it is not being bounded, so we call this as your free variable, and this is bounded. This is called your free variable. So these are all called free and bounded variables in the sense that for all x, p of x implies q of xy means x is a bounded variable, whereas y is what? Y is free variable, x is bounded variable. So this is, and another example I can give you is, see, this is what I mean. See, for all x, p of x implies, let me q of x, something I write here like this. So you see that here again, you see that I am telling that for all x, p of x, I will put it in this way. Okay, no problem. For all x, p of x implies q of x. But you see this quantification, see, this quantification comes here only for what? This part. For this only you are getting the quantification. So the quantification, the variable for which, so the variable which has been quantified will be called as a bounded variable. The variable which has not been quantified will be called as a free variable. For example, you see that this x is a variable which is quantified, so it is called a bounded variable. Here again you are taking it to x, q of x, but nothing, this q of x, this quantification is only for this, therefore this x is a bounded free variable. So this is what we mean by a free and a bounded variable. If a quantification comes for a certain variable, that variable will be called as a bounded variable, and the variable for which there is no quantification will be called as a free variable. Can you catch my point? I'll repeat this. In a particular given compound proposition, that is in predicate calculus, if the quantification comes for a variable, it will be called as a bounded variable. If the quantification does not come, quantification in the sense there exists or for all x, if that comes, if it does not come, either there exists or for all such quantification, if they do not come for a variable, such variable will be called as a free variable. Are you able to catch this point? Then say this one, and another important point that I want to drive at is this one. See, I put it like this: negation for all x, p of x. No, this will be equal to, you know what is the meaning of this? Read this. for all x, see this one even you can write like this, see. Negation, now read this, negation of for all x p of x. That means p of x is some propositional function and that x is, don't bother about that, x is taken from universe of discourse. So you see that x is taken from universe of discourse and p of x becomes a propositional statement. And I say that for all x and that x is given a value for p of x. That is the meaning of that. If you negate it, let me suppose that I gave you an example that p of x means x is greater than or equal to 5. Okay, that particular statement was correct. Now if I say that negation means, what does it mean? Just now a few minutes back I explained to you, if you want to say that something is wrong, or false, at least one example can be given to say that it is wrong. So that is all. So in the same way here what it means that, see, for all x means you must say negation of for all x and negation of p of x. How should you write this? So read this, for negation of for all x p of x. So you see that what I write here is that negation of for all x, this one, see, negation for all x will be there exists x and negation of p of x. Now you read this. Say negation of x means there exists an x for which negation of p of x is true. See, I gave you that 4, 5 domain for which I can get there exists one element 4 for which that particular statement is not true. So you see that this is, and in the same way negation of there exists p of x is a negation of there exists of x and negation of p of x. So this is equal to for all x negation of p of x. So this is what we mean by that, and these two are very, very important. And another thing I want to mention here is that, see, this is just slightly out of this one, that is here you mean you see that we have written here, that is you know the De Morgan's law. So all whatever I taught you in propositional calculus, that holds good. All the laws and everything, whatever I taught you as tautological implications, then other things, whatever I taught you there, they are all true for, what is that, laws of propositional logic, propositional calculus are true for predicate calculus. Propositional calculus means what? Simply statements, propositions. Here predicate calculus means what? Propositions which are all quantified, which are what? As I told you, they become quantified statements. Variables will be coming and variables will take values from a domain and they are quantified also. So we are studying, doing problems on this type of propositions, quantified proposition, everything will be called as a predicate calculus, otherwise they are called propositional calculus. So you see that De Morgan's law. So whatever the laws that you apply for propositional logic or calculus, they are applied to this also. So tautological implications, equivalences and other laws of algebra, everything holds good here. Okay, now De Morgan's law. See, we know that De Morgan's law, I taught you like this: P negation of P Q is identically equal to negation P conjunction negation Q. Negation of P conjunction Q is equal to negation of P, this one. So this is, now you see that what I say here is that negation of P union Q is identically equal to negation of P conjunction negation of Q. So this is what we have. So this implies that negation of P disjunction Q, two-way implication if and if only, negation of P negation of Q is identically two-way. See, what does this mean? If two statements are equivalent, what does it mean? If two statements, even, see, this is of different. If two propositional functions, that is propositions, here I am taking only proposition. If two propositions are equivalent, then that is their two-way implications, that is their if they are connected by this if and if only, then this value will be equal to your T. That means this becomes a tautology. What I mean is that if you have a statement like negation of P union Q is equal to negation of P conjunction negation of, if these two are true, then this implies that their biconditional statement, that is what I mean. So if two propositions are equivalent, then their biconditional statement is a tautology. What is that? If two propositions are equivalent, if two propositions, compound propositions, let us suppose, let me put it in that way. If two compound propositions or formulas are equivalent means what? You change the variables of the coming in that, in whatever way you want, they will be identically equal. They are identically equal. Okay, you see that these two are equal. That is, if you take negate P union, you take P union Q, you negate. Negate means what? You get the negation, you negate it and you get the values. And do this negation of P, this one. Then you see that since these two are equivalent, then it means their biconditional statement is a tautology. This I will prove here. Just see how I do this. See, what I do here is that, see, whatever I do here, because while doing this predicate calculus, I do this because whatever I do here, they are applied to this. For example, you see that P, Q, then P union Q, negation of P, then disjunction Q, then let me put it in this way, then we will take negation P, then negation Q, then negation of P conjunction Q, and I take this A biconditional statement B. Now you see that this is true means this is true, negation of this will be false, negation of it is F, and this is F, and what is this F union in conjunction F is F. Then T, F, and this is again T, and negation is what? F, and this is F, and this is T, and their conjunction, F conjunction, this is your F only. And come to this, it is F, T, and this is F means what? This is T, and this is what? You get this to be your negation of this, this is F, and what is negation of P is T, and this is F, and negation of these two conjunction is what? F. And come to this F, and this is F, and this is T, and this is T, and this is T, and this is T, and this is also T. Now you just see that can you see this? Negation of P disjunction Q, these two values. I told you that they are equivalent. FF, FF, TT. So they are equivalent statements. They are equal. Now you take the biconditional statement. F biconditional F. See, F biconditional is what? F biconditional F is true. F, see, F biconditional F is true because true. If this is true, false, this is also false. If this is false, then, so one implies the other. If first is F, the second is F. The second is F means first is F. That means they each imply the other in the same way, and therefore it is a true statement. So this is true. Come to this again, FF. This is true. FF, true. Now TT, again T. So what is this? For any statement you take, this is so. It says that it is a tautology. Can you get this? So this is called a tautology. So they become tautological statements. That means negation of P union Q is equal to negation of P conjunction negation Q. They are equivalent. If they are equivalent, in the sense you change what P and Q in any way you want. You give the values, but you will find that they will always be equal. That means what? This is F, this is F, this is F. For this TT, it is FF. For this TF, this again they are what? FF. And for FT, again FF. For FF, it is T, and this is also T. And you see that if that is so, then the biconditional, say I have written here. A means this one, B means this. So A biconditional statement, B is, see everywhere it is 2. That means what? If two compound propositions are equivalent, then their biconditional statement is a tautology. So they will ask you these things. So you see that this is what we get. Now, so you see that we have got this fully done. And let me, so these are whatever you study here in propositional calculus, we just transform or study in the same lines the predicate calculus also. Okay. Now let me pause on to the next one.